First of all, welcome to my presentation on scaling ETH infinitely without UX and liquidity fragmentation. And the first thing I want to say, as any good programmer, I fucking hate the word infinite. Nothing scales infinitely. It's a marketing thing, right? We can call it scaling ETH linearly according to instances of rollup or execution sharding. So first, a little bit about me. My name is Daniel Lumi. I'm a researcher and consultant working with L2 protocols, ZK protocols, privacy and DAOs. The majority of what I do right now is decentralizing provers and sequencers, as well as interoperability in the fractal ZK landscape. Today, we'll be talking about how blockchains currently scale, how we can get them to scale infinitely, what do blockchains look like in the future, and when is that going to happen? So why this talk? Um, Again, I'm a programmer, so I would look at blockchain and think this shit doesn't scale. It really doesn't. Like if we ever won 100 million monthly active users, good luck. That shit's gonna burn down and the fees are gonna be really expensive. But with some of the newer developments that we have that we'll be talking about today, we actually are starting to have an idea of how we can scale blockchain so everyone can use it. So how do blockchains currently scale? And we'll compare sort of Web 2 scaling to Web 3 scaling or blockchain. So how does Web 2 scale? So maybe you want to go to Apple's website, you want to pre-order the newest phone, and the first 1,000 users go on the server, and it works just fine, right? But now 2,000 users want to pre-order the phone, and all of a sudden, the server burns down. It doesn't have enough resources to serve everyone. So what Apple actually does is they kind of have like an osmosis. They copy the state of the first server onto another server. And then the first 1,000 people get it from the first server, and the next 1,000 get it from the second server. Cool. So now everyone can pre-order. And so essentially, 2 scales linearly according to the amount of resources on the network. So if you have a server with X resources, you get 1x scaling. If you have 2 of them, you get 2x. If you have 4 of them, you get 4x, right? So it just keeps scaling more with the amount of boxes you stick in. So how do blockchains scale? And the whole sort of point of blockchain is we don't want to trust anyone. Like there's no single source of truth. So essentially we have to have every single node re-execute every single transaction over and over again around the world, right? So just to give an example of this is, let's say you have a network with 3,000 nodes. Each block takes 5 seconds to execute. Essentially you have 4 hours of essentially servers re-executing the same transactions over and over again just to reach consensus. And this is honestly a bit wasteful, but it's how it works. Right? So the way blockchain scale is, again, let's say you have 1 transaction. You see that first blue dot there. That's how much work it takes to execute that block. If you have 2, essentially you get linearly more time to execute each transaction. That's a bit simplified because every transaction is a bit different. But the more transactions you have, the higher node requirements you need, essentially. But the problem is in Ethereum and Bitcoin, we want a normal computer to be able to execute this block. So we essentially artificially cap the amount of transactions that can be in a block. That's around 15 to 30 transactions, depending on the complexity on Ethereum. And so in a blockchain, sort of, let's say you have 1 node, you have 1x scaling. Let's say you add another 10 nodes, you still only have 1x scaling. Let's say you add 1,000 nodes, you still have 1x scaling. It doesn't scale with the amount of boxes added to the network. It just makes it more decentralized and censorship resistant, but it doesn't actually scale anymore because you still have the same amount of gas. So we came up with this concept of Ethereum 2.0, right? And the goal of Ethereum 2.0 was to essentially break Ethereum into 64 shards, right? And each of the validators, the validator committee would be split into 64, and they would take turns validating different shards, right? But the problem with this was that every single one of those shards was less secure than the entire blockchain. Now you only have 1/64th of the validator set validating that shard. And the other problem was like we didn't really have a good plan of how do shards talk to each other, especially atomically. We had some ideas, but they weren't so good, and it would have broken a lot of applications. So we scrapped Ethereum 2.0, and that made Vitalik very sad. So how do we scale ETH infinitely without UX and liquidity fragmentation? So we move to this sort of concept of roll-up-centric Ethereum, right? And the idea is we still have shards, but instead of the base layer being sharded, we can essentially have a shard on top, and essentially they have their own state, and they submit the data as well as a proof later onto L1. And this way, every single one of those shards actually still has the full security of Ethereum, right? This is also execution sharding, it's just done differently. And I won't go into much on how L2s work, because if you're here, hopefully you know, but essentially the idea is a separate blockchain can run its own transactions off-chain and then submit the data and a proof onto Ethereum to prove that it's running correctly. And with rollup-centric Ethereum, essentially, this is kind of made up numbers because each rollup is a bit different and the choices they make is different. But let's say you have Starknet on top of Ethereum. Now you get 10x scaling on Ethereum. Then you have OP and Scroll and all these other ones. Maybe you get 40x scaling on top of it. And this is great, again, because every single one of those shards inherits the security of the full L1 validator set. But there's lots of problems with just spinning up more and more L2s, right? So we'll walk through these problems now. So let's say all of a sudden Scroll does amazing and every single Ethereum user moves to Scroll. At some point, the gas on Scroll will actually go higher than Ethereum L1. And if the gas keeps going up more and more, what's the point of L2s? We didn't really fix anything. We're just shifting around the problem, right? So the crackpot team at Starknet came up with this idea. We'll build L3s, L4s, L5s, more L2s. And in a way, this is actually not a bad idea. It just needs some interoperability plays, right? So this plan, everyone gets a layer. You get a layer, you get a layer, we all get layers. Yay! And this concept is called recursive ZK rollups or fractal hyperbridges. And the idea is that when you actually bridge from L2 to L3 to L4, you actually don't really have any additional security assumptions because all of those layers use the same circuit for the bridge, right? You might have some issues with frozen funds, but the security is not really affected, right? And this is sort of like how bridging would work in this landscape, right? So instead of if you're on that L5 and you want to bridge to that other L5, you don't actually have to make a bunch of different bridge transactions. The key point is all of the assets for all of these rollups are actually locked on ETH L1, the same contract that all of them uses. So you essentially don't actually even have to do bridging. You just do fancy accounting. You just mark it's here now, right? And this way you can just kind of bridge funds directly over with the security of the L2. And this is the same concept, but instead of going vertically upwards, essentially Optimism and Polygon will go horizontally sideways. So just build a bunch of L2s using the same common bridge. And cool, so now we fixed L2 fees. The state of any of those chains is not going to get too big, and if there's too many users, you can just keep splitting up new instances and gas fees stay low. But we still have this issue of like, now we have a bunch of L3s and L2s, like how do we do interoperability between them? Right, and here's an example of like, let's say you have some funds on Starknet L2 and you want to move them to ZK Sync L2. You can just bridge them over with like, I don't know, what's the shittiest bridge you can think of? Multi-chain? No, don't do that. That's cross-chain. That's the same as going from Ethereum to Solana. Just don't do L2 to L2 bridging, right? So what we can actually do is we can essentially Starknet can have a contract where essentially it batches a bunch of users' withdrawals into one transaction, then sends them directly through L1 to ZK Sync's native bridging contracts. And then you essentially move a bunch of funds all over at once, right? And that's great. Now we have like a proper trustless bridge, right? But that's asynchronous. It's going to be much more expensive than the shitty cross-chain bridges, and it's kind of slow. Even with ZK protocols, you'll probably have to wait some hours. So essentially, a bunch of projects are now moving forwards is into this sort of fractal scaling, right? The idea is all of those different L3s, L2s are on the same bridge contract, right? And again, all the funds are locked into that one bridge contract with the fancy accounting, right? So now you can just bridge over funds, right? Yeah, I mean, yes, but again, it's asynchronous. It's not the same as having a monolithic chain. And then there's issues where if you're doing a bridge transaction from Coinbase to Optimism, there's plenty of time to front run you before you do that, right? So essentially, one way we could do this, and this was sort of most people's original ideas, we just have one beefy sequencers that executes Coinbase L2, Optimism L2, and all the different L2s, right? And now it's composable. We get atomic composability again. And, well, there's no cross-chain MEV. There still might be MEV, right? But the problem with this is that now there's a giant beefy node, right? And in L2's, node requirements are not as big of an issue as L1 because it doesn't affect security at all. But we still want to keep it decentralized for censorship resistance and liveness, right? So that's not great. If you get 100 L3s and all of them are the size of Ethereum, you're going to need some beefy ass computers to do that. And you can call this one beefy sequencer to rule them all. Not a good idea. So another example of how we could do this is we can have one main sequencer that just orders transactions. It doesn't execute them. Ordering transactions is very cheap. And then every one of those L3s or L2s has its own sequencer, and those come in and later execute those transactions in a lazy way. And essentially they just agree, we insert this transaction here, right? And now we do have pseudo-atomic composability, and all three of those nodes are very small, right? But there's still the cross-chain MEV issue, or the cross-fractal MEV issue. And the problem is because, let's say, Optimism is not aware of Coinbase's state, you might actually start that transaction, and by the time that the next L2 executes it, it might just fail, right? And then you have funds stuck, or it was bad UX. So then we can add in a sort of proposer-builder separation with, for example, Suave, right? And now you have a bunch of Suave builders. They run sequencers for each of the nodes that they want to have interoperability with, right? And now you can actually, like, because they know the state of each chain, they can actually guarantee you that that transaction will execute on both sides and it is included at the right time. So it's, again, atomically composable and there's no failed transactions. But you still have MEP, right? The Flashbot builders or Suave builders might see your transaction, see there's a chance to take some money from your swap, and they might still front run you, right? So now we can have lazy execution plus proposed builder separation plus a new transaction type called a threshold encrypted transaction. And essentially, you submit your transaction, the block header is still public, but you encrypt the block body, right? And then in block n+1, so the next block, essentially they agree to reveal the transaction. In this way, you can't be front run or sandwiched because it's already included in the chain. You can still be back run, but that's actually beneficial forms of MEV. Front running and sandwiching, not good, regardless of what MEV people tell you. So now you have L3, L2 design where you have atomic composability, small nodes, and no MEV, theoretically. And a cool sort of thing that you can build on top of this is, let's say, like currently, without having those features, let's say Uniswap has its own L3, and you do some swaps there. Like, cool, it works. But again, the problem is maybe there's too many people now swapping on Uniswap L3, and so you get high transaction fees again, right? What we can kind of do, and this is early in design, is again, all the liquidity is in the L2 for the L3s. So you can actually dynamically shard the state of Uniswap over and over again into small chunks. And then from a UX point of view, we can just show you like the full bounce through the RPC. We can just show you how you swap one ETH to USDC, even if it's swapping across many different shards. And hopefully they can add them dynamically and then delete them dynamically. And now you get your swaps and not high transaction fees. Okay, so we fixed interoperability, right? But now we have all these L3s, L2s. We need a lot of data. And that's going to be much more data than we want on Ethereum because, again, we want the nodes to be small. So this guy, Dankrad, thought about this issue. And he thought, We have something for that. In fact, every single data center already uses this. We just haven't adopted it yet. That's called erasure coding, right? So this is a sort of explanation of danksharding with erasure coding and data availability sampling. It's not entirely accurate. This is to give you a mental model. So in the current schema, every single node on the network needs all of the data. And right now in Ethereum, that's about 1 terabyte, right? So what we can do with danksharding instead is each of us keeps a small chunk of the data. But now the problem is, like, what happens if this guy disappears? Now you can't continue the state. So we actually keep our data, plus we keep another 50% or 25% of erasure encoded data, so the other block's data. So now if this guy disappears, we can come together and reconstruct the state of his missing data, right? And so how do you make sure all that data is still available? Because now you only hold a small amount of the data, but you don't know if that guy's holding his data. And if the data disappears, that's really bad because we can't continue the state anymore. So we use something called data availability sampling. And right, so let's say you have 100,000 blob data points. You essentially, what you do as the validator is you take a random number between 1 and 200,000. Then you ask the network for it, and at this point you've done one random check of data. There's about a 50% chance, there is a 50% chance, that all of the data is available, right? This is just a game of mathematical probability. By the second sample, there's a 25% chance that someone's lying about holding the data. And by the time you do this 30 times, there's a 1 in a billion chance that anyone could have lied. And maybe you can do this 60 times just to make sure. So it's essentially next to impossible to withhold data. You know if it's available or not. Cool. So now he knows. But what happens if the data disappears, right? And okay, we can check that the data is gone, but that doesn't help us a lot. Well, essentially, the validators in the full danksharding need about 75% of all of the data to be able to reconstruct the missing data, right? Which is good. And the important piece of this is, like, it's not great for consensus if this happens, but this is a one of n security assumption. So if there's a single honest node anywhere in the world, and they don't even need to be honest, we can check if they're honest, that holds the full state, we can reconstruct the data and fork the protocol and continue that fork automatically. Cool thing about danksharding also is sometimes we have these shitcoins or NFTs that essentially clog up the gas fees of Ethereum. With the blob transaction, there's a separate gas market. So even if there's a random NFT mint, it will not affect the ability of L2s to be able to actually submit the data onto Ethereum. Cool. So now we have all these fixed. So ETH is infinitely scalable, right? Yay! And no. We still need to make some changes to L1 as well. We haven't forgotten about L1, even though people think we have. Like, we're still working on those changes. And so the first example of this is parallel execution and localized fee markets. So there's this thing that we can already declare in a transaction, which is what state we're actually going to touch in a transaction. And if we essentially enforce this or optimistically execute it that way, we can actually parallelize execution sharding. So if I send Orist 1 ETH and someone else sends someone else 1 ETH, you can execute those on 2 separate machines. But you still can't do that for a shared state. Like if 2 people are swapping on Uniswap, that needs to be run synchronously. And then another thing that we can sort of implement if we force access list is something called localized fee markets. It requires some other changes than just access list. So again, if there's a random NFT mint, right now, everyone's gas fees goes up. With localized fee markets, we can essentially isolate that. So that contract that's doing the NFT mint, that gets very expensive, but Uniswap fees stay the same. And honestly, we probably won't do this on L1 because it breaks some contracts, but at least we can implement this on L2 level. Then we have this concept of statelessness. And Ethereum actually has in the roadmap already the plan to change from Merkle trees to Verkle trees. And just to give an explanation of why statelessness is good is Essentially, in today's world, every single node needs to download all of the data of Ethereum. That's about 1 terabyte right now. And you can't load that into memory, so you need that on a hard drive. A normal hard drive's not fast enough, so you need it on a SSD. And 2 terabyte SSDs are a bit expensive, especially if we want anyone in the world to be able to run it. So with statelessness, essentially, we supply full witness data as well as the actual block. And at this point, you can essentially run a transaction with having very little of the previous state, about 1 terabyte, which also fits on a phone. And you can continue running the chain. So now we can have much more computers and even phones actually validating the network. ZK for L1, this is not a if, it's a when. We will make Ethereum L1 work with ZK, right? And again, this is sort of going back to that blockchain scalability bit. Again, this is how normal blockchains work right now, right? With ZK rollups or ZKL1, it's a bit different, right? So the prover needs to essentially run every transaction that's quasi-linear. That's actually not super accurate, the chart there. And then every single other computer on the network just has to verify the transaction. And actually, because proofs are easily parallelizable, we can actually have a bunch of small computers running the proof, and then everyone else just verifies them. So now all the roles on Ethereum are very, very light. And that difference between proving to verification is essentially the scalability factor we can get on Ethereum L1 with ZK. And again, while you're running now nodes with ZK-L1, now that they're executing the transactions, they also create a proof for this. And this way, instead of every node needing to re-execute every transaction, they can just verify that every other node was honest and did their part correctly. This, in combination with statelessness, essentially allows even your iPhone to be a full node in this network, right? Then there's this concept of enshrined rollups. And this is a bit difficult because we essentially need a lot of agreement on consensus on essentially design for this. It's very much under active research, but essentially the idea is we can have these sort of enshrined rollups on L1, where essentially the rollup is essentially governed by the consensus of the L1, right? Again, this would imply like one type of verifier contract on Ethereum. It's very much under the work, but essentially we could get rollups to inherit the entire security and consensus rules from L1. So how does this look in what are blockchains in the future like, right? And the idea is, like, the nice thing of L2s, L3s is we can do a bunch of these experiments and prove them out over a long time and then take the best parts and merge it into Ethereum 1.0, right? And at some point, if we figure out the interoperability between shards and how we make ZK proving much faster, we can essentially make a new execution sharding design on Ethereum where, for example, each contract would be its own shard, and we could scale ETH also infinitely horizontally. And so when token, just kidding. When scalable, coming soon. Give us 10, 15 years. Like, it's, again, very much under active research, but when we get there, you'll see Ethereum Vitalik clap. It's beautiful. You want to see this in real life. It's really funny. And the point of this is, unlike some blockchains, Bitcoin, Ethereum is actively taking steps to build towards the future of the blockchain. No protocol is perfect from the first time, and blockchains are certainly not scalable right now. But if we can figure out some of these issues, we can actually massively increase the user experience of blockchains and make it work for everyone in the world. We talked a lot about ZK in this. For a long time, for many years, there was a very select group of us nerds that loved ZK. And with the invent of ZKL2s, all of a sudden everyone's talking ZK this, ZK that. But if you ask cryptographers, for example, Ariel, or other like friends of mine, they'll go into polynomial commitments and Fried-based recursion. So I made a presentation to try to explain how ZK works without talking about math much. We also talked about bridging in cross-chain as well as within those L3, L2 shards. That's a very complicated topic just on its own. So if you want to learn more about the security compromises with bridges, you can watch this. And also L2s have their own sort of security issues. This is actually with yours. This is a panel from ETH Gathering that we did, just talking about some of the issues that L2s have with security and how do we improve some of those things. That's it. Thank you. You can follow me on Twitter at ZKLumi. I don't do a lot there. We have Toggle for shit posting, but I do post stuff occasionally there.